The other one is fine, apparently. Yeah, yeah. I'll do the install while we go. It should go fairly quickly. All right. So basically, what I want to do is go through all of that, right? It's a bytecode inspired and influenced for browsers for execution. Now, key thing to understand is that WebAssembly does not standardize a runtime. To go back to your question of earlier, they do not standardize a runtime. The whole point is to define a bytecode that can be hosted in a variety of different environments. The WebAssembly group is working on a runtime, but it's intended to be simply a reference implementation to let you know how this stuff is supposed to work, what it's supposed to look like. Right? They've defined a number of toolkits along the way, which we'll talk about as we go, that will help people, particularly those people who want to implement WebAssembly, to understand how this is supposed to work. Because they can write specs all day long, but in some cases there will be weird edge cases that the specification doesn't cover, and that's where a reference implementation will be helpful. But in terms of what will the performance of a WebAssembly runtime be like, that's entirely up to that particular runtime. There will be some that will be not optimized at all, such as the reference implementation. They want to be correct, not fast. And there will be other implementations where they will emphasize speed over, hopefully not too badly, over correctness in some cases. Or any places where there are gray areas, there may be some room for innovation, which will get closed later, et cetera, et cetera. The key thing is that second bullet point. WebAssembly is designed to be standardized across all the browsers so that we can stop using JavaScript as a compile target. That is literally, if we're going to sum this up in a single nutshell, that is the goal that we're trying to get to. Fast, safe, portable semantics. These are some of the buzzwords that they use in the specification document. Well-defined hardware language and platform independent, so it works regardless of where you are. Effective, efficient and portable, that's a typo. Representation, ideally easy to inspect and debug. We'll look at what the text-based format looks like in a little bit. It does not look like what you would expect it to. Talking a little bit about the history. In 1997, I was actually working for Pacific Bell, which was one of the big telecom companies in the United States. And I remember when browsers were, they were standardizing on HTML 4.0. You think you have it hard now, folks. Try doing all this lovely UI work when you really have nothing but tables and divs. That's it. That's all we had. And JavaScript was present in the browser, but quite frankly, and PacBell was one of these places, it was considered to be a security risk. And as a matter of fact, one of the things that you did when you were building a website in 1997 is you made sure that your site worked even if the users had turned JavaScript off, which many users were, if not suggested, then required to do. We hated JavaScript. We absolutely despised it. It seems like the worst, ugliest hack ever, primarily because it did not look at all like Java. Now, fast forward 20 some odd years, today we understand that the relationship between Java and JavaScript is roughly the same as the relationship between ham and hamster. We get that now, but we didn't then. Browsers ran applets. And Sun in particular was generating a lot of interesting buzz around the idea of being able to execute code client-side in the browser. Now, back in 97, as we were just ramping up the whole internet thing, we were just starting to ramp up the idea of building quote-unquote web applications. The early idea was that we were going to run Java applets in the browser as our user interface, that were communicating over the network via Corba to servers back on the server end, which would then go talk to our relational databases. And it seemed like a good plan in the beginning. This is part of the reason why Sun for so many years held on to Corba inside of the JDK, because there were a number of early adopters who still, to this day, continue to run that architecture for reasons that I just can't possibly understand. But the biggest problem with Java was the fact that it had to be in the browser in order for this to work. And of course, the other thing that happened around this time is Sun and Microsoft decided that they were not going to get along anymore. Sun sued Microsoft over its implementation of Java. Specifically, they said, you have added some extensions to Java which are not a part of the Java standard. And Microsoft said, so what? We still run Java code as is. And Sun said, yes, but not every Java implementation can run code that makes use of those extensions. And Microsoft said, so what? And Sun said, so we sue you. And the Department of Justice got involved and blah, 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 blah. A bunch of legal fees later, Microsoft was ordered to remove Java from their browser. That was really the death knell of applets. Nobody would really talk about running any sort of client-side executable code for another decade. The whole idea was do everything server-side, push everything to be generated from the server. All the execution should be on the server. The browser should basically be nothing more than a dumb terminal that knows how to display HTML. In many respects, this was our generation's attempt to go back to mainframes. You joke, you laugh, but that's literally what a web browser is during this time frame. It's basically a 3270 terminal plus audio and visual, so we can get basically 3270 plus porn. In 2006, a few brave, hardy souls decided that they were going to try to change the equation and start using JavaScript to do more interesting effects. And Jquery was born. And Jquery was really the first effort at using modern JavaScript. Modern meaning we're actually using the language the way it was designed rather than trying to force it into be something that it was never intended to be, that is to say Java. And Jquery and its ability to execute client-side and its ability to do a number of interesting effects begins to turn a few people's heads and go, you know, maybe this JavaScript stuff isn't all that terrible after all. And in 2011, I had the privilege to sit down, because I live in Redmond, Washington, and Eric Meyer, who's a very famous Haskell and other functional mindset programmer. 2011, Eric Meyer suggested that JavaScript should actually be a target for various compilation languages. It was the first time I had ever heard anybody suggest that. And quite frankly, I thought the man was nuts. I absolutely thought he was a crazy old Dane who had no idea how this was going to work. I mean, why would I want to compile from a language like C# or Java into a higher level language like JavaScript? I mean, normally when you compile, you want to get closer to the metal, not further away from it. And he said very bluntly, JavaScript is ubiquitous because browsers are ubiquitous, and you're never going to get people to agree on anything beyond what's supported in JavaScript in the browser. And after so many years and several attempts to revitalize the whole browser applet concept, I'm looking at you, Flash, I'm looking at you, Silverlight, I'm looking at you, a bunch of other projects that never got off the ground. Ultimately, what we have come to realize is that the browsers run JavaScript and the end. And so people started talking about targeting JavaScript. Eric in particular had a research project inside of Microsoft called Project Volta, which ran for about a year or so. And actually his goal was, let us write code and let us, based on the code you write, split the code, target JavaScript, and send some of that JavaScript to the client browser, send some of it to the server, some of it to both places if it's supporting shared code, and let's just let the user pretend, the user, that is to say the programmer, you all, let's just let them ignore the fact that there's a network in between. Now, Volta obviously didn't ship. It was done in 2012, but there were a number of interesting projects that emerged out of that, including the IL to JS project, which allows you to take .NET assemblies written in intermediate language, IL, and compile them, transpile them over to JavaScript. Now, I don't know that Microsoft actually does anything with this, but it definitely got a couple of people thinking. In 2013, a number of folks said, what if we actually do some sort of halfway measure? What if we had a JavaScript library that mimicked being a CPU? had registers in the stack and all of that sort of thing. And what if we targeted that rather than, human readable JavaScript? And asm.js was born. And this is when we first started to see the Emscripten toolchain targeting asm.js. And actually, it got to the point where asm.js was pretty fast. The Mozilla browser, which supported asm.js starting with v22, knew how to do optimizations based on the asm.js code that it was seeing, to the point where you could take the Emscripten toolchain, you could grab the old Doom source code, the first-person shooter, compile it with Emscripten, and run it in your browser. And that was pretty fucking cool, because it definitely proved the idea that we could take C++ code as untouched. They did not have to make any source changes to the Doom source code, compile it and run it in the browser, and it was as fast as I remember playing Doom. As a matter of fact, it was faster than me, because I kept dying, and that's the only thing I can think of why I would keep dying at Doom, is the machine's running too fast. Why are you laughing? Don't laugh. My gaming skills have not atrophied at all as I got old. In 2015, people said we should actually own this collectively. So asm.js, the people who were involved with it, got roped into being a part of a community group owned by the W3C. And in 2015, they officially formally started the work that, as I said, completed in 2018 last year. Supported in the 4 major browsers, we talked about that already. There are a number of different specifications, the biggest one being the core spec, which is actually accessible via GitHub. So if we wander over, well, let's just do this. Nope. Nope. This should be easy to fix, he said. Try that again. There we go. So webassembly.org is the website where all of the WebAssembly stuff lives. And if we go to WebAssembly GitHub, there is a project page for all things WebAssembly here. So in particular, there is a spec. This is where they actually write the specification document and generate the various PDF and docx formats, et cetera, et cetera. So if you want to track the specification, you can obviously just clone this particular project and watch the changes that come in. We'll talk a little bit more about some of these other projects, but they're definitely doing as much of the work as possible in the open on GitHub, which is commendable. All right, so if you want to get started with WebAssembly, generally speaking, like I said, you're not going to want to write WebAssembly by hand. You're going to use some other language to do that. The usual tool of choice, the usual entry point, is a tool called Emscripten, as I mentioned before, which, if we want to download, there's 2 basic ways to do this. One is to grab a zip file. The other one, which is generally the more preferred approach, is to do a lovely git clone and such. Oops. So, oops. Oh, sorry. There we go. All right. So once you've got the Emscripten SDK on your machine, you're not done. Because the SDK, this is intended as a thin shell that they can version into. Specifically, you use the MSDK script file to install various versions of Emscripten. Okay? Now this is going to take a few minutes because it's pulling down some binaries and then unpacking them so we can watch the percentages increment there. The Emscripten SDK, as I said, makes use of a lot of existing C++ toolchains. So this is actually building on top of G++, LLVM, CLang, et cetera, et cetera. Part of what they're doing with this tool is they're trying to keep all of those in sync. Now, when I did this on the other machine about an hour ago, it will report an error that there is a slight version mismatch between various parts, between CLang and LLDB and so forth. We'll see if that still holds. I might have pulled it down in the middle of an update. we'll see. But at the very least, my demos were still working on that machine a few minutes ago. So if it doesn't work, it's their fault. All right. So blame the no. They're wonderful people. I don't want to suggest that we should all go get after the AV guys for any reason whatsoever. Now, having pulled down the latest bits, the other thing we have to do is we have to activate them. This is basically required to set up the necessary symbolic links to point to the version of the toolchain that you have just downloaded. The whole point of this is so that you can have multiple versions side by side in the event that you want to work with like a 1.0 release and then some later beta release. So far, there's really only the one master release, and that's the one, that's the one that I work with, is whatever is marked as latest. But at some point, as WebAssembly gains a little bit more traction, as Emscripten starts targeting additional features inside of the WebAssembly toolchain, this may be important. All right, so now, lastly, in order to bring all of those symbolic links and paths and so forth into my shell, I will source msdk env shell, and I should be able to run emcc, which is the Emscripten C compiler. And yep, there's that version warning. Notice it's saying 1.30.33, 1.30.31, 1.30.31. They're off by like 0.02 in the most minor part of it. So I think we can safely ignore this. And then it's also complaining that we're not giving it any input files. All right, well, let's go. Demos. And RigaDevDays. All right. Let's give it some code to work from. Specifically, you guys all know what this is, right? Yes? Come on, be honest. How many of you have never seen C code before? Show of hands. Yeah, you're all just ashamed to admit it. This is C code, folks. As a matter of fact, here. It's not C code until you start working with pointers, right? Right. All right. So, I've got some C code here. There it is. Actually, let me, because I know this screen cuts off a little bit there. All right, so emcc hello.c. It's thinking. Did I mention that it wasn't necessarily optimized for speed? What's fundamentally happening here, if you look at the messages, notice the .bc extension. That's bitcode. That's LLVM bitcode. That is, in some respects, kind of like the bytecode for LLVM, except it's not intended to be directly executable. It's intended to be essentially the intermediate output for the LLVM toolchain, which then gets passed to the assembler in LLVM to be turned into actual native executable code. And what we get out of this, a.out.wasm, which is 42K in size. Notice there's also a.out.js, which is 102K in size. What they've done is they've actually not only compiled my hello world, but all of the necessary supporting C library code so that this will work. So if I've got the right version of Node, which is currently 891, which should be late enough. There we go. That's about as sexy as these demos get, guys. So, if you're not impressed by that, I think Venkat is doing something reactive over there and, whatever. Anyway. Yeah, so that's basically, well, okay, hang on. I should be more clear. There is actually a more interesting demo that we can do, which I will just cut and paste from their website. Whoops, not on this page, on the tutorial page. Right there, see, there's hello world. By the way, we can also do it with C++ if anybody really feels like we want to do the 90s more justice. But let's grab this bit of code here. Let's create a new file. We'll call this hello SDL.c. SDL, for those of you who are not familiar, is a library, a native library called Simple Direct Layer. This is actually a library that is designed to abstract away a number of the differences in terms of doing graphics and audio and video output. As a matter of fact, a number of the more popular game engines use SDL as the underpinnings for doing the actual work on the operating system. So for example, if you've ever played the open source game Wesnoth, Battle for Wesnoth, that's written all in SDL. There are a couple of game engines, I forget which ones, that use SDL as its target. Ruby Motion, Dragon GTK, these are all game engines that use SDL as the underlying layer. So what we've got here is we've got something that's going to display basically a multicolored rainbow box. And we want to do it in the browser, but I don't want to have to deal with a.out and so forth. So what I will ask Emscripten to do, using the traditional C format of -o indicating the output file, I'm going to ask it to put it into hello.sdl.html. Oh, you're right. Thank you. See, this is why pair programming works. Oops. Because it thinks that I put it into a CPP file. That's what the extern C will do. And that should fix that. Yep, we have a hello SDL. Now, if I just open this HTML file in my browser directly, we're actually not going to see anything because it's actually going, the HTML is written to do an XHR, basically an AJAX style lookup back to the server to go fetch the JavaScript and WASM files. So what I have to do is I have to run this inside of a web server. And if you have Python installed, then we can run the simple HTTP server, which they have an example of in one of these little blockouts here. And I always forget the exact, it's like -m, come on. There we go. That's what I'm looking for. So we'll run this very simple web server on my machine. So now it's listening on port 8080. Thank you, Python. You have served your purpose well. HTTP localhost 8080 hello SDL.html. Boom! Okay, that is literally the sexiest these demos are going to get. Okay? Well, I take that back. Hang on. There is one more thing that we can look at. If I go back to my slides here. So, yeah, we did basically all of this. We did this. We did this. We talked about SDL. Oh, yes. Here we go. Let's go grab this. I hope it's still there, because otherwise I'll be very disappointed. Oh! Hang on. Maybe Google can help us. WebAssembly tanks demo. Nope. Well, shit. This has just not been a good day for this particular talk, has it? Anyway, they had a very simple demo demonstrating more of the 3D capabilities, because again, most of that was the SDL library. And what the WebAssembly and Emscripten folks have done basically is written a adaptation layer for SDL into the browser, so that when you run something that uses SDL, you're actually tapping into OpenGL in the browser, which is called WebGL. And it can do music, and it can do all of the things that a good game library should do, as long as you know the right SDL calls to make. Now, that is something that the Emscripten folks have done. The WebAssembly folks are still working to define a number of interoperability points, API points, for interacting with the browser as a whole. Right now, browser interoperability is pretty crude by comparison. And again, we'll go into some of that as we go. Hopefully, they'll get that fixed fairly soon, particularly because it's a fascinating demo because it was actually written in Unity, which is this really big, heavy 3D augmented reality, virtual reality game development environment. And if that can compile down into WebAssembly bytecode, then we can literally see a whole generation of first-person shooter type games, as well as other equally performance-intensive games, written in Unity, compiled to run in the browser natively with WebAssembly, or compiled to run on your mobile device, because Unity knows how to cross-compile to either the Android or the iOS platforms as well. So there's definitely some interesting movement there with respect to that. When we talk about a WebAssembly interpreter, what they describe is a virtual instruction set architecture. Essentially, the WebAssembly bytecode is not designed to be run natively on any particular CPU. The whole intent is that it be embedded somewhere, interpreted, and run. Now, interpreted here does not mean that they have to read one opcode and then execute it. Interpreted simply means the bytecode is not designed to be run as is on any particular hardware platform. There's going to need to be some layer of software that knows how to understand the WASM bytecode. But in the same way that Java code can be just-in-time compiled and we get much better performance out of it, WASM could definitely be just-in-time compiled. And as a matter of fact, we can use a lot of the same techniques that are used in the JVM for a WASM-based interpreter because they're both stack-based virtual machines. Everything is done in terms of pushing things and popping things off of a virtual execution stack. So if you've ever looked at Java bytecode, then a lot of the WASM bytecode will be exceedingly simple by comparison. If you've never looked at bytecode, well, you will not be able to say that in about 20 minutes, because we will go look at that bytecode in just a second. The WebAssembly execution, they talk about it happening in 3 distinct phases. Decoding, which is to say, let's take that format and unpack it into an internal representation. Let's validate to make sure that it all looks good and behaves correctly. And then execute, which is broken into 2 parts, instantiation and invocation. These terms are only necessary if you want to start diving into the mechanics of how WebAssembly works. If you just want to be able to compile stuff into WebAssembly and just assume that magic happens and it all just works, cool, we're done. Fill out your evals and you can still go catch the last of Venkat's reactive session. But if you want to understand deeper details about how WebAssembly maps to the browser, how you can map languages into WebAssembly, that's where this semantics begins to become important. Now, the specification offers up a number of terms, which I figured was just better to go through as a glossary. The first is the notion of module. A module contains definitions for functions, tables, and linear memories, all of which we'll go through in just a second, as well as mutable or immutable global variables. Definitions can be imported, meaning a module can depend on another one and make use of the symbols that are defined in the first. Can be exported under one or more names, can define initialization data. This is all pretty standard stuff for anybody that's trying to build a language. Initialization data, for example, is if I want to say int x equals 5 in my language of choice, well, that 5 has to live somewhere, and there has to be some bit of code that sets that 5 into x whenever we enter that function or whenever we start that program. That is the role of your initialization data. It's generally pretty simple and straightforward. Modules can define, for initialization data, they can also define a start function that is automatically executed. That start function will be either the function that performs all of that initialization, if this is intended to be a library module, for example, or that start function will be literally main, where your program will begin execution. Code is organized into separate function. Function takes a sequence of values, returns a sequence of values. Functions can call each other, including recursively. This sounds pretty much like a stock function from any procedural language of choice. By the way, when they say function can return a sequence of values, currently the WebAssembly specification says that sequence of values is limited to 1 value. The intent is that they will open that up later when they fully specified the semantics, but I mentioned earlier they want to start small and grow rather than trying to get agreement on every last little thing just to get to a 1.0. A table is an array of opaque values of a particular element type. It's kind of like an array in some respects, but the use of a table here essentially is almost like name-value pairs so that we can look things up. So modules, for example, can have a table that lists all of the functions that are present in this module. And as a matter of fact, that's the only real use for tables at this point, is untyped function references. Now, at some point later, again, they will expand this to allow for potentially global exported values, or they will allow it to allow us to define, for example, some notion of class or object that could be understood across modules. But right now, it's just a table of functions, the end. Linear memory is a contiguous mutable array of raw bytes. In other words, this is your heap. This is whenever you want to allocate memory, you want to create a linear memory. And as a matter of fact, the WebAssembly specification has bindings already for how a host program written in JavaScript could create a linear memory and make that available to the engine for execution and use. Most of the interoperability between outside WebAssembly and inside WebAssembly will come through these linear memory. And you'll see what I mean in a little bit when we talk about it a little bit further. Traps are basically execution, right? This is essentially like a signal on an operating system. This is a way of the program inside of the WebAssembly engine to signal to the host that something has gone wrong. And in some cases, traps could be recovered, and in some cases, they cannot. Kind of depends on the agreement between the host and the code that's running. The WebAssembly specification, however, wants to make sure that there is a way for that to happen. They want to make sure that that is specified and defined so that my host program could, in fact, capture that trap and potentially handle it and allow execution to resume, et cetera, et cetera, et cetera. The embedder is the host. That's your browser, that's Node, or that's some program that you write if you write your own WebAssembly engine. One of the things that the WebAssembly group is working on is, in fact, a couple of WebAssembly implementations. So if we go back to, back to here, and if we look at the list of projects that they are working on, for example, binary N, compiler infrastructure, and toolchain library for WebAssembly and C++. So if you wanted to write your own engine, here is a whole bunch of supporting code that you don't have to write. But further on down this list here, let's see. Oh yeah, by the way, we'll talk about this one in a second, Wabbit. That's literally what they call it, Wabbit, the WebAssembly binary toolkit. And matter of fact, let me shut you down. And git clone. We'll let that pull that down. But here, for example, they have an example of a WASM that will do just-in-time compilation as a prototype. So if you are interested in building your own WebAssembly engine, this is a good place to start. And let's see. I have not actually looked at this one yet. I'm kind of curious as to what language they're writing it in. Yeah, C++. Bunch of C++ propeller heads involved in the WebAssembly project for a variety of reasons, mostly historical. All right. So that's our basic terminology. If you understand those half a dozen terms, you basically understand everything that the WebAssembly specification talks about. The instruction set for WASM is very straightforward. Again, this is a stack-based virtual machine, so everything we do will be done in terms of the execution stack. If I want to add two numbers together, for example, I will push the first number onto the stack, I will push the second number onto the stack, I will then execute the add instruction, which will pop those two values off the stack, add them together, and push the result onto the stack. It's a very, very simple way of abstracting how we pass parameters around. Everything is done in terms of an execution stack. If I call a function, the function will expect that the top of the stack will hold all the parameters it is expecting in the appropriate order. Now, generally, this is the work of the compiler to make sure that all the bytecode lines up and puts everything in the right place. But if you're going to operate at this level, and if you're going to write assembly script, there is a language out there that will let you write in native WASM, then you're going to have to understand the stack. You're going to have to make sure you balance the stack so that if you get a result back, it's your responsibility to pop it off the stack in order to consume it, and or leave it there because you're using that as the first parameter to the next function call you might make. It's your goal to make sure that the stack always balances out to 0 at the end of the program. If not, you have a stack leak and bad things can happen. Modules are made up of 0 to n elements, each of these things. Imports, exports, types, functions, tables, etc., etc., etc. Okay? And it's very, very low level. Now, any and all of these may be empty, and as a matter of fact, the simplest module written looks like this. And you say, dude, what are those rounded brackets doing there? And I tell you, that's because the WebAssembly text format, also known as WAT, uses S expressions. And you say, what the hell is an S expression? Well, basically it's Lisp. It's Lisp or Scheme, take your pick. It's that exact format. Lots of irritating, silly parentheses. Now again, remember, this format is intended basically to be easy to use, not necessarily easy to read. Excuse me. When we start talking about module and structure definitions, generally everything is done by index, which is a 32-bit unsigned integer in size. There is no point to having negative indices. This includes all of the locals inside of functions or any labels inside of a function. If you have more than 2 to the 32 functions or 2 to the 32 locals inside of a function, we have bigger problems. So generally, this should not be any sort of limitation because functions should not be that big to begin with. The type will define a vector of function types. Again, the only thing that WebAssembly defines right now are functions. Later, if we get classes and objects, presumably they would extend the notion of types to allow this to be a vector of function types or object types or class types or structure types or tuple types or whatever else they feel the need to define for interoperability purposes. The start indicates the start function. Again, start will basically be a keyword inside of the module declaration, and it will say the start function, the one that you need to invoke when this module is instantiated, is number X in the function table. So here, for example, we have a slightly more reasonable module. It depends on an imported function from a module called imports, and it takes that and assigns that to this $ imported func. Now, the $ is just my convention. That's to indicate that that's something that I'm writing. That's just purely my convention that a couple of other folks in the WebAssembly world have used as an example. Notice that I then have a type $_func. That's my type table. I have one type of function, a function that takes nothing and returns nothing. I also have another type of function right underneath it that I've given the name ii_I, indicating that it takes 2 integers as parameters and yields 1 integer as a result, which you can see defined with the func, param i32 close, result i32 close. I then export one function by the symbolic name add, and the function I wish to export is the function add, which is defined right below it, which is of type ii_I, has 2 parameters, 0 and 1, with the result i32, and now we get to actual bytecode. Here I do a local get, meaning I want to pop this off the stack. I do another local get, and I pop that off the stack. In this case, those are the parameters that are coming in, so it's not coming off the stack, it's actually coming off of the parameter stack, which is slightly different than the execution stack. And having pushed those guys onto the stack, I call add. Those 2 are added, the result is placed on the stack. That's where I want it, so I just end. Any questions so far? Congratulations, you are all bytecode assembly programmers. You can put this on your resume. Okay? This is literally what Java bytecode looks like as well, by the way. They have almost the exact, if you write an add function in Java, the bytecode for that function will look semantically exactly similar to this. Pull the first parameter, push it on the stack, pull the second parameter, push it on the stack, add the two, and in the case of the Java bytecode, it will actually say ret the value to make sure that gets pushed onto the stack if it's not living inside of a local. Now I want to export a function called call_i to indicate that I want to call something. And in this particular case, this is a type nothing, so it takes nothing and returns nothing. Notice I push the constant 42 onto the stack, and then I call imported func. Well, whatever that function does, it's getting a 42 as a parameter. And again, my function does not return anything, so there's nothing to push onto the return stack, so we're done here. And then last, of course, we have main, which is also a function that takes nothing and returns nothing. In this case, I'm pushing 128 and calling that imported function. Now remember, there's nothing magical about the name main in WebAssembly. What is magical is whatever function I identify as the start. And that's what that last line in the module does. It indicates that the start function for this module is main. We have just defined a WebAssembly module. If I were to take this text, as a matter of fact, actually, let's do this. Let me check one other thing here real quick, because I want to see if I have to build those tools, so we'll turn that loose for a little bit. And we're going to grab this module code. Oops, I want to be in code here. We're going to call this module, or let's call it demo.wat, like so. And then let's go back to the previous slide and grab the rest of this module definition, like so. So we now have a wat file. And once the Wabbit toolkit finishes compiling, okay, hang on. I remember what I'm doing wrong here. Nobody look. What? Git clone submodule. All right, I may have to just punt on that one. Sorry about that. What we can do is we can use the utility in Wabbit to compile. There is actually a utility called wat to wasm. Wasm is the compiled flavor, the binary flavor. Wat is the text flavor. We can turn this into wasm code, which we could then load and execute in Node. Just to go through the bytecode really quickly, there are basically 4 numeric bases on a 2-dimensional axis, 32 versus 64-bit, floating point versus integer. Those are your base for any sort of operation. So if I want to push a constant value, I have to decide what type of constant do I push. Is it a 32-bit int, 64-bit float, whatever. We saw that earlier. i32.const says I want to push this constant value onto the stack. Same thing would be for 64, float 32, float 64. There are a number of operations that manipulate the stack. Push is pretty obvious. Drop says I want to throw away whatever it is that I just popped off or whatever. Select says basically I want to pick either A or B, depending upon whether or not the C value is equal to 0 or not. That's basically an opcode that does an if. We also have counting the number of leading or trailing 0 bits. This is important for some low-level operations. We have all your classic mathematical operations, add, subtract, multiply, divide. And the divide and remainders are basically whether this is unsigned or signed mathematics. We can shift some bits around. We can do and or style logic. do some mathematical absolute negation, ceiling, floor, truncation, nearest, square root, min, max. And then the last 6 are how all of your comparisons work. Take the 2 elements on the top of the stack and compare whether they are equal or 0, compare whether they are equal, not equal, less than, greater than, less than equal, or greater than equal. Again, very, very straightforward bytecode operations. There's operations to be able to set and get globals and locals. Again, all of this is done via indexes. And then local.t basically says, I want to grab a local and push that onto the stack, but I also want it to return. In other words, we're going to push this value onto the stack twice. The Java bytecode set calls this the dupe instruction, and it's very helpful because frequently I want to get the result of a value and use it multiple times, so we'll dupe it frequently in order to save us a couple of operations. Load and store know how to push things into and out of the linear memory. We can get the size of a given memory. We can also grow it up to whatever the limitations of the host are. Control operations, no op, pretty straightforward. Unreachable is essentially code. This is an opcode that will immediately trigger a trap. This is what you put into your code in order to make sure that this code, in fact, never executes. I actually encourage you to do the same thing if you ever are in a code review with me and you have a catch exception and then you have curly bracket and then a comment. This should never happen. Guess what? I'm going to insist that you put a system.exit into that whatever code should never happen, so that if it does, the whole virtual machine terminates. Usually when I do that as part of a code review cycle, people go, wait. What do you mean you're going to just up and quit everything? Well, if this should never happen, then there's no reason to be worried, right? And that's when programmers start saying, but what if? Well, what if? Maybe you should put something else in that empty catch block, you bloody moron. Branching instructions, the call instruction, which we already saw, hosting it. There is a WebAssembly object inside of your node environments. It's also present inside of the browser environments. This will give you the opportunity to grab and load WASM code. So for example, let's see, here. This is actually some node code that will load and execute some form of WebAssembly code. So up top, we see an environment variable that basically defines the raw environment. We're defining one linear memory of being 256 bytes in size. We're defining a one table containing just one element anyfunc. We create a uint array. That's basically going to be the linear memory that we work from. And then we can put any sort of imported functions into this imports block below. So notice here I have imported func, which does console.log. Yes, this is the same imported func that my module from earlier is depending on in order to be able to execute. Then I instantiate that module, and once that returns a promise, so once that's finished, we can look at what we got back in terms of the result, which should be the module, right? And then we can get the instance of the module, because the module is basically code, but it doesn't actually do any of the initialization until we instantiate the module. If you're starting to get the sense that modules are kind of similar to classes in some very, very rough way, that's not too far off the mark, except that many languages will actually say that an atomic unit of deployment, such as a .NET assembly, or if we start talking about Kotlin files, they will often have some sort of surrounding construct that we can have. Well, basically that's where the global variables will live, and that's where the global functions will live. WebAssembly is doing much the same thing here. So it would not be a huge stretch to see them create a refinement of module, call that a class, allow it to have both data members and function members, and boom, lo and behold, we have just created a primitive object system. Assuming that all works, then we can get the exports out of the instance, which will include the add function that we defined in that module. And at that point, we have it available as a local value, which we can just invoke, and it will hopefully give us 4 back. Hopefully. If you want to do this in the browser, same basic story. Notice the use of the browser-defined fetch function to go get that WASM file. And then once it's there, again, we use the WebAssembly.instantiate. Once we've got that, and here I've shortened up all of the previous code into basically the one line to go to the result, go to the instance, go to the exports, get the add function, and then invoke it. The tooling, I'll just rip through this fairly quickly. We've talked about Wabbit. We've talked about binary N. Binary N is really only important if you're planning to write your own WebAssembly environment. Wabbit is useful if you're going to dive at all into WebAssembly at any level, just to be able to look at the compiled results and make sure you see what's going on. There is actually an IDE for WebAssembly, and in it you can write C code, Rust code, Watt code, or assembly script, which is an assembly language for WebAssembly, which is written by a third-party company, and I'm not quite sure what their business model is going to be, but there you go. It's available, and it's right there in the web in your browser. There are a number of tools that come as a part of Wabbit. The one that I wanted to use earlier was Watt to WASM to compile my text mode into binary mode. We can also go the other direction. One of the things that I found very interesting was to take some C code, compile it with Emscripten, then take the WASM and turn it back into Watt, and holy cow, there's a reason why that thing is like 45K in size. There's a whole bunch of support code that goes into even the simplest hello world. There's also a WASM interp, which is a WASM interpreter. Again, not performance optimized. This is heavily, heavily, heavily focused on just making sure we get the semantics right. By the way, if I'm not mistaken, all of Wabbit is written in a programming language called Objective-Camel. It's a functional object hybrid language, which was actually the immediate predecessor of F#. So it's actually really, really favored by people who are doing compiler tools, because compilers are very functional in nature, but we also have the opportunity to do objects, and OCaml compiles entirely into native code. So that's a win. A couple of other supporting utilities to do various things depending upon what you want to look at, as well as to convert a WebAssembly binary into a C source and header. Again, this is primarily for round tripping if you're writing tools. Validate to JSON, opcode count, spec test interp. These are all utilities that are used by the WASM committee as they start writing and exploring and defining some of these things. I mentioned binary N already. There's some binary N tools here. And again, most of these are only useful if you're going to be a C++ developer that's targeting WebAssembly in some fashion. There is some third-party tooling. I already mentioned assembly script. Basically is a build-off. It converts the binary N toolkit into JavaScript and then uses it from within whatever environment you're running this in. There's also a third-party company that is doing a commercial open-source C++ compiler. That's not a typo. That is actually how they describe their product. It's commercial and it's open source. I'm not quite sure what their business model is, but they are definitely on the leading edge in terms of C++ functionality compiling into WebAssembly. So if you're a C++ developer and you're really hell-bent on getting into WebAssembly right now, today, goddammit, then I would definitely consider contacting these guys and see what their licensing model looks like. One of the things I want to point out as we were whipping through that definition of WebAssembly bytecode, did you see a string type? Did you see a character type? Both of those are missing from the WebAssembly toolkit. If you, in fact, write some WebAssembly code and you want to take a string and pass it back to the JavaScript host, like the browser, you actually have to put each character into an array in linear memory and then hand an index to linear memory back to the JavaScript code, who will then have to go into that byte array and character by character copy that into a string before you can actually use it as a string inside the rest of your JavaScript code. That is not exactly interop friendly. If you write C++ code, Emscripten knows how to create some JavaScript helper functions to make this interoperability story easier, but that's Emscripten's own code. If you use Rust, same story. If you use Kotlin or anything else, they will each have their own interoperability elements. and everything is still being defined in terms of ints and floats. I personally think that you should be looking at and tracking WebAssembly, but not putting it into production right now. Not in 2019. Possibly in 2020, if and when WebAssembly 1.1 is defined, if and when they add a string type, because otherwise the interoperability story here is going to be very, very language specific, and any desire to write some WebAssembly code that could be called from other languages, like JavaScript running in the browser, is kind of a non-starter because everybody's going to have their own interoperability details. So I would definitely keep an eye on this. The other thing that I'm actually kind of curious to see is SDL, by virtue of the fact that it's a low-level graphics toolkit, it would be very easy to define a graphical user interface toolkit in SDL. As a matter of fact, most games do that themselves. And if I'm able to compile SDL into WebAssembly and run that inside of the browser, then theoretically, I could build my own custom user interface. I don't have to be limited by whatever the browser gives me. If I really want to have a drop-down box that I can type in, but it actually pops up a circle rather than a physical drop-down list, well, that's exactly the kind of thing that SDL will allow you to do. As a matter of fact, it'll even help with some of the animations by doing some of the transposition and so forth. That is exactly the kind of thing that a powerful graphics toolkit will give you. And the fact that I can compile SDL into WebAssembly makes me wonder how long before we start experimenting with creating our own user interface toolkits for running inside of a web browser so it doesn't look like every other web application on the planet. Particularly if you work for a creative digital agency, this is a huge opening as opposed to writing JavaScript code that writes to WebGL directly, which can definitely be something that only a handful of people on the planet can really do effectively. Now, again, you would be writing all that SDL code in C++. How many of those people are around? I don't know. It's worth watching, but I would not consider shipping anything in it. Do not ship before December 31st of this year. And if you want to do it in 2020, hey, you're on your own. Thank you for your patience. Thank you for your time. Enjoy the rest of the show.